Welcome back, everyone, to Saltwater Stories.
It's great to be exploring with you again.
Today, we're going on a really grand adventure. Imagine slipping beneath the surface of the big blue ocean, leaving all the sunlight far, far behind, and exploring this world that's usually totally hidden from our eyes.
Yeah, a world that's under enormous pressure. It's freezing cold down there and just completely dark.
It really is the planet's biggest and maybe strangest neighborhood.
Definitely biggest. And what we're talking about today, it connects every single part of that huge ocean.
Right, from the tiny little plants waving in the sunny bits right at the top.
All the way down to the creatures living in the absolute darkest places, kilometers below the surface.
And this amazing thing, it's a never-ending event. We've actually mentioned it before, haven't we? When we talk about some deep-sea creatures.
We have. It pops up in so many ocean stories because it's just that important.
It kind of looks like a slow-motion blizzard, maybe. But it's definitely not made of wind or rain.
No, not at all. But it is the food source. You called it a floating buffet before, and that's perfect. It feeds the weirdest, coolest, most energy-saving creatures on the whole Earth.
It really does seem kind of magical how this simple-sounding thing feeds a whole world down there.
It helps keep our planet cool. And
Yeah.
even, believe it or not, helps build the land we walk on. It sounds incredible, right?
It does. But we should probably give a little warning.
Yes. The magical part. Well, it's also tied to something that's, let's be honest, just a little bit gross.
Yeah. Just a tiny bit. So are you ready? Let's reveal the secret. Today, we are dedicating all our attention to the longest, gentlest, never-ending snowfall on Earth.
It's called marine snow.
Marine snow.
And that name, it's just perfect. Imagine this continuous, really slow motion shower, tiny, delicate little bits just drifting down through the water.
All the time.
24 hours a day, 7 days a week, year after year. It just never, ever stops. And this slow, gentle fall, this is the life support system for the deep ocean, which, remember, is the biggest home, the largest habitat on our entire planet.
And without this floating food.
Everything down there would just starve. Simple as that.
Okay, so before we get into the secret recipe for these amazing snowflakes, we have to talk about how anyone even found out about this magical blizzard.
Right, the discovery story. Because for thousands of years, people knew the ocean was deep, sure. But they had absolutely no idea what was happening way down below once the light disappeared.
So we need to travel back in time, back to the 1930s, and meet two incredible explorers. There was a scientist, a naturalist named William Beebe.
And his partner, an engineer named Otis Barton. And Beebe, he was, well, obsessed is probably the right word.
Obsessed with what?
With one single mission, to see the deep ocean with his own eyes for the very first time in history. He wanted to go deeper than anyone had ever gone before into that world of crushing pressure.
Of like a normal submarine wouldn't work back then. Like,
Yeah.
Not strong enough.
Exactly. They just couldn't handle the pressure that deep. So Beebe and Barton, they invented something totally new, something amazing. It was called the bathysphere.
Bathysphere, let's break that down. Bathy means deep.
And sphere means ball.
So a deep ball. Okay, picture this, everyone. A giant, really heavy steel ball. But it was only about 5 feet wide inside. Imagine squeezing into that.
Super cramped. And the walls were made of thick steel, inches thick. And it only had 3 tiny windows made of quartz, this super strong glass, like 3 inches thick. That was the only way to see out.
And they couldn't just climb in and close a hatch?
Nope. They literally had to be bolted inside from the outside.
Yeah.
And the whole ball, this bathysphere, it just hung from one single, very long, very strong steel cable.
Just one cable, that was everything.
That was their lifeline. It carried the wires for their telephone connection to the ship above, their electricity for the light, and most importantly, their air to breathe.
Wow. And no engine, no propellers.
None at all. It was just lowered down into the blackness, like you said, like a giant fishing lure dangling on a line.
That sounds unbelievably dangerous.
Oh, it absolutely was. They were going into total darkness, miles down. If that one single cable snapped, well, they'd be lost forever, instantly crushed by the immense weight of the water above them.
Beebe actually wrote about it, didn't he? He said being inside felt like being the first person on the moon. So isolated, so dependent on this one machine.
Exactly. And then in 1932, off the coast of Bermuda, they did it. They had their big moment.
How deep did they go?
They reached a world record depth, 2,200 feet. That's deep. Way, way past where even the tiniest bit of sunlight could reach.
So they were in the midnight zone.
The midnight zone, a place no human had ever ever seen before. So they turned on their powerful searchlight, peered out of those tiny, thick quartz windows.
What did he see? Was it just black?
At first, maybe just blackness, but then BB described the world outside as boiling with light.
Boiling with light.
Uh-huh.
But it was pitch black.
Bioluminescence. The darkness was actually filled with creatures making their own light. Glowing squid, fish that flashed like little lightning bugs, sparkling jellyfish everywhere. It must have been absolutely breathtaking.
Wow.
But then, right there in the beam of their searchlight, he noticed something else. Something strange. Something moving very, very slowly and constantly.
What was it?
He described it as a steady, unceasing vertical fall of minute, pale grayish particles. Just stuff.
Drifting down.
Yeah.
Drifting past his window in the total darkness.
Huh. Little bits falling down.
Yeah. He didn't know what it was. But that constant, gentle downward movement.
Yeah.
It looked exactly like snow falling outside his window back home on a winter day.
Ah, so that's where the name came from.
That's it. So right there in his logbook, his scientific journal, he wrote down a name for this visual effect he was seeing. He called it marine snow.
William Beebe, the first snow watcher.
Very first. The first human to actually see the lifeblood of the deep ocean, this constant shower, in its natural form. That's such a cool story. But it wasn't just a cool sight, right? It was important for science.
Oh, hugely important. Because before Beebe went down in the bathysphere, scientists kind of knew something must be falling down there.
How do they know?
Well, they used nets to catch deep-sea animals way down deep. And those animals obviously had to be eating something, right? But they couldn't figure out what. They tried towing nets through the water column itself, hoping to catch the food.
Oh, wait, you said the marine snowflakes are delicate?
Exactly. Super fragile, like really gooey, crumbly clumps of stuff. So imagine dragging a rough net really fast through the water.
Or you would just smash the snowflakes into mush.
Totally. Obliterated them. So the scientists using nets, they knew the ingredients were down there, the little dead bits, the tiny shells, but they couldn't see them all clumped together, falling gently like snow.
So they missed the snow part.
They missed the snow. It took Beebe, sitting perfectly still in his bathysphere, gently looking out the window, to reveal that the food source for the biggest environment on Earth wasn't just random bits floating around. It was this constant, connected blizzard.
And that beautiful name he came up with, marine snow, it just stuck.
It's stuck forever. It's perfect.
Okay, so now we know how it was discovered. Let's finally get to that secret recipe. You warned us. It's a little bit gross.
Yeah, well, yeah. The science word for one of these snowflakes is an aggregate, which just means a clump or a collection of things stuck together.
And if you could, like, gently scoop one up and look closely.
See, it's a total mix match. A hodgepodge of detritus.
Detritus. Fancy word. What's that mean?
Detritus basically means waste or scraps or leftovers. Dead stuff, essentially. So marine snow is mostly a mix of tiny dead plants, little bits of animal poop, and sticky slime, all glued together.
Okay, dead plants, poop, and slime. Got it. Let's break down that recipe. Like, what are the main ingredients to make a good snowflake? Where does it start?
Okay, ingredient number 1, the tiny plants. Or more specifically, their skeletons. We're talking about phytoplankton.
Phytoplankton. We've talked about them before. They're like the microscopic, tiny floating plants of the sea, right?
Exactly. You can think of them as the grass of the sea. They live right up near the surface, in the sunny part, and they soak up the sun's energy through photosynthesis, just like plants on land. And there are billions and billions, trillions of them.
And they make little skeletons.
Uh,
Or shell.
yeah, tiny hard parts. Some types, called diatoms, build these beautiful, intricate little shells out of silica, which is basically glass.
Wow. Glass houses.
Right. And others, called coccolithophores, build tiny little plates around themselves made of calcium carbonate, which is chalk.
Like blackboard chalk.
The very same stuff. So when these tiny plant-like creatures die, their little glass shells and chalk plates start to slowly drift downwards. They're super light, like tiny bits of dust floating in the water.
Okay. So that's the base, the starting point. Like maybe the flour in our snowflake cake.
Good analogy. That's the base ingredient. But just those tiny shells alone, they'd sink incredibly slowly. They'd take maybe months or even years to reach the bottom. They'd get eaten or dissolve way before then.
So they need something to make them heavier, faster.
Precisely. Which brings us to the, perhaps the most important part for sinking speed. Ingredient number 2, the poop bricks, or scientifically, fecal pellets.
Goop bricks. Okay,
Yeah.
tell us about the poop bricks.
Right. So there are also tiny animals living near the surface called zooplankton. Think of them as the tiny bugs or maybe the cows of the sea. They eat the phytoplankton, lots of them, thousands every single day.
Munching away on those tiny plants.
Yep. And as they digest the plants, they take the energy they need, and then they package up all the leftover bits, including those hard little shells and plates, into these dense, heavy little packages. Poop. Fecal pellets. But these aren't just waste. They're absolutely vital. Because they are packed with carbon and other nutrients, they're like perfect little energy bars dropped from above for the deep sea creatures.
And they're heavy.
Yes, that's the key. They are much, much denser than the single tiny plant cells. So these poop bricks act like tiny little weights or engines inside the snowflake. They make the whole clump sink much, much faster. We're talking sinking maybe hundreds of meters every day instead of just a few centimeters.
Okay, so we have tiny plant skeletons and heavy poop bricks. But how do they stick together? If I threw dust and pebbles in the air, they wouldn't just clump up.
Excellent point. You need glue. And the ocean has its own special glue. Ingredient number 3, the sticky slime, or ocean glue. Scientists have a fancy name for it. TP. That stands for transparent exopolymer particles, but sticky slime is way better.
Sticky slime. Okay, where does the slime come from? More poop.
Not exactly poop, but it is ooze. It's a sticky mucus that's secreted or oozed out by both the phytoplankton themselves and also by the bacteria that live on them and eat them. It's kind of a waste product for them, but for making snow, it's brilliant.
Slime is glue.
Exactly. This slime is special. It's sticky like glue, but it's also a little bit stretchy, maybe like snot.
Ew. Okay, ocean snot glue. Got it.
Perfect. And that sticky, snotty force is what makes the whole system work. It causes all those other ingredients, the tiny dead shells, the heavy poop bricks, even bits of dust floating in the water to bump into each other and stick together, to clump or coagulate.
Coagulate means clump up.
Yep. Stick together into one bigger blob, one marine snowflake. Without that sticky goo, you wouldn't get snowflakes, just tiny bits floating around too slowly. The deep ocean would totally starve.
So the slime is the secret binder. Okay, we have skeletons, poop bricks, and slime glue. Is that it?
Almost. There's one more category, ingredient number 4, the hitchhikers and the ballast.
Hitchhikers. Like things catching a ride.
Exactly. A marine snowflake isn't just dead stuff falling. It's actually a tiny living island as it sinks. It's swarming with millions, even billions of bacteria and other tiny microbes like fungi.
What are they doing on there?
They're living on it and eating it. They're the decomposers. They're hitching a ride down, but they're also slowly breaking down the snowflake as it falls, recycling some of the nutrients.
Okay, so living hitchhikers. What about the ballast? That sounds like something on a ship.
It is. Ballast is just a word for extra weight that helps something stay stable, or, in this case, sink faster. So the ballast in marine snow is the non-living, heavy stuff that gets mixed in.
Like what? Rocks?
Tiny bits, like tiny grains of sand or silt that get washed into the ocean from rivers, or even dust that blows off deserts like the Sahara, flies over the ocean and falls onto the surface.
Desert dust ends up in marine snow. No way.
Absolutely. And this heavy ballast, these tiny bits of rock and dust, they add crucial weight. They help the snowflake overcome the water's resistance, the stickiness of the water, and especially that goop parachute effect we'll talk about. It helps ensure the flake sinks fast enough to get past all the hungry mouths waiting in the middle layers.
Wow. So the final recipe. Tiny plant skeletons, heavy poop bricks, sticky ocean glue, living hitchhikers eating away, and tiny bits of sand and desert dust for extra weight.
That's our marine snowflake, ready for its big journey.
Okay, let's follow one of these snowflakes now. We know the recipe. Let's track its journey. Yeah. You mentioned the ocean's like a giant skyscraper.
Yeah, or maybe a huge apartment building with many, many floors. These floors are stacked in layers called zones, and the marine snow, that's the non-stop 247 food delivery service, starting right up at the penthouse suite.
And dropping food off on every single floor below.
Exactly. So our journey begins right at the top, layer 1, the penthouse, also known as the sunlit zone or the epipelagic zone.
Sunny penthouse. Makes sense. How deep is that?
It's the very top layer, down to about 650 feet or 200 meters. This is where all the sunlight penetrates, so the water is generally warmer and it's bright. This is the only floor in the whole ocean building where there's enough light for plants or phytoplankton to live and grow.
So this is where the snowflake ingredients are made.
Precisely. The vibe here is sunny, busy, lots of life. This is the snow factory. This is where the phytoplankton bloom. They get eaten by zooplankton. The poop bricks are made. The slime oozes out. Everything gets mixed together.
And the sticky glue makes the flakes start to clump up.
Right. And as soon as the flake gets heavy enough, it starts to sink. It begins its long, slow fall out of the bright penthouse and down into the next layer.
Which is?
Layer 2, the snack bar, also called the twilight zone or the mesopelagic zone.
Ooh, twilight zone. Sounds mysterious. How deep is this layer?
This stretches down from where the sunlight zone ends, about 650 feet, down to about 300 feet or 1,000 meters.
Does light get down here?
A little bit at the top of the zone, but it fades really fast. It goes from maybe bright blue to a really rich, deep blue, then kind of a dark indigo. And then by the bottom of this zone, it's pretty much total darkness. It also gets much colder, and the pressure starts to get really intense.
And you called it the snack bar. Why?
Because this layer is packed with animals that are experts at finding food in dim light or darkness. These are the gatekeepers, you could say, or maybe the toll booth operators for the sinking snow.
Waiting to grab the snacks as we fall past.
Exactly. Food is much scarcer here than up in the sunny penthouse. So the animals in the twilight zone, fish, shrimp, jellyfish, squid, they intercept and eat a huge amount of the marine snow that drifts down into their lair, maybe up to 90%.
90%, that's almost all of it.
It's a massive amount. This layer is where the real race happens. The great race against time for the snowflake.
If it's light and sinks slowly.
It gets eaten, gobbled up. Its nutrients, its carbon, get used and recycled right there in the snack bar, relatively close to the surface.
But if the snowflake is heavy, full of poop bricks and ballast.
And sinks fast. Then it has a much better chance of racing past all those hungry gatekeepers, escaping the snack bar and continuing its journey downwards.
Okay, so if our brave little snowflake makes it past the snack bar gauntlet, where does it go next?
It plunges into the deep, deep darkness.
Layer 3, the midnight zone. This is everything below about 3,300 feet or 1,000 meters, all the way down to the abyssal plains, the very bottom of the ocean floor, which can be miles deep.
Midnight zone. So absolutely no sunlight here. None whatsoever. It is pitch black, 24/7. It's also freezing cold, often just above freezing temperatures. And the pressure, it's immense, like having dozens of elephants standing on your thumbnail, crushing pressure.
And the food.
This is the crucial part. That little bit of marine snow that didn't get eaten in the snack bar, maybe only 10% of what started falling.
Yeah.
That 10% is now basically the only source of food for almost all the life down here in the midnight zone and below. Everything is waiting for this slow delivery from above.
Wow. Only 10% makes it. And how long does this part of the journey take? The fall through the midnight zone?
It's a long, long fall. Depending on the size and density of the snowflake and how deep the water is, it can take weeks, sometimes even months for a single flake to finally reach the seafloor.
Weeks or months just falling through darkness. And wasn't there something new you mentioned? Something scientists just found out about this journey being even slower.
Ah, yes. This is super recent, like 2023 recent. Scientists use these incredibly advanced underwater microscopes and cameras to actually follow individual marine snowflakes as they sank in the ocean, like tracking a single package delivery.
Wow. What did they find?
They found that the snowflakes sink much, much slower than the calculations based just on their size and weight predicted. Something was slowing them down.
What was it?
Remember the sticky slime? The TT?
Yeah, the ocean glue.
Well, as the snowflake falls, it actually trails behind it this sort of invisible halo or tail of that sticky, slimy mucus. It leaves a slime trail.
A slime trail, like a snail.
Kind of. And this mucus trail interacts with the water around it. Water itself is a bit sticky, right? It has viscosity. So this trailing mucus halo creates friction or drag. It acts like a tiny, invisible parachute trying to slow the snowflake down.
A goo parachute. That's amazing. But wait, if it slows the snowflake down, that's bad for getting food to the deep sea, right?
Exactly. It's a real problem for the delivery service. This goo parachute effect, this extra drag from the slime trail, can actually double the amount of time it takes for a snowflake to sink through the water column.
Double the time, so it spends twice as long falling through the dangerous snack bar zone.
Precisely. Twice the time for those hungry gatekeepers, the shrimp, the fish, the jellies, to find it and eat it. It gives them a much better chance of catching the snow before it escapes to the deep.
So this discovery means maybe even less than 10% of the snow makes it all the way down.
It definitely makes scientists rethink the numbers. It changes our understanding of how much food and, importantly, how much carbon actually reaches the very deep sea and gets locked away. That journey is much tougher, much slower, and much more likely to be interrupted than we ever realized.
Okay, so the few flakes that do survive the long, slow, goo parachute-hindered journey finally reach the freezing dark bottom. What happens then? Who's waiting down there?
Well, since there are absolutely no plants growing down there in the dark, every creature living on or near the deep sea floor has adapted to survive on whatever falls from above. They are all detritivores.
Detritivores. Detritus eaters.
Gunk eaters.
Dunk eaters, exactly, or scavengers. They've evolved these amazing, sometimes really weird ways to find and eat the marine snow with maximum efficiency. They can't waste any energy.
Why do they have to be so efficient? Just because food is scarce.
Scarce, and it arrives unpredictably. You might get a little flurry of snow, then nothing for days or weeks. So if you spend a lot of energy swimming around actively hunting for these tiny flakes, you'll probably burn more calories than you gain. You'd starve.
So they have to be smart about how they get their food, using as little energy as possible.
Exactly. Passive feeding strategies are key. Let the food come to you.
Okay, let's meet some of these amazing deep-sea snow eaters. Who's first? You mentioned one with a really scary name.
Yes. Perhaps the coolest name in the ocean. The vampire squid from hell. Whoa! Vampire squid from hell.
That sounds terrifying. Suck blood.
Hey, great question. Its scientific name, Vampiroteuthis infernalis, literally means vampire squid from hell. And it looks the part. It lives way down in the dark twilight and midnight zones. It's usually this dark, velvety red or black color. It has these huge eyes, proportionally the biggest eyes of any animal on Earth, actually, to catch any tiny glimmer of bioluminescence. And it has this cloak-like webbing between its arms that it can pull up over its head like a vampire's cape.
Wow, it sounds like something from a monster movie.
It really does. But here's the twist. The name is totally misleading. Scientists studied them and looked inside their stomachs, and guess what they found?
Blood, tiny fish.
Nope. Marine snow, bits of detritus, mucus, fecal pellets, crustacean parts, basically gunk.
No way. The vampire squid from hell eats falling trash.
Pretty much.
Yeah.
It is the only known cephalopod that's the group, including octopus and squid, that does not hunt and eat live prey. It's a detritivore, a passive marine snow eater. So it's not a terrifying hunter at all.
Oh.
How does it catch the snow if it's not hunting?
It uses an amazing, super energy efficient technique. It has 8 arms like a regular squid, but it also has 2 extra super long whip-like thin threads called filaments. It can be way longer than its body.
Filaments.
Yeah.
Like fishing lines.
Exactly like fishing lines. It
It's-
just drifts passively in the dark water, conserving all its energy, and it stretches out one or both of these sticky filaments. They just hang there in the water waiting.
Waiting for snow to bump into them.
Precisely. As the marine snow drifts down, it gets stuck to the sticky filament. When the squid feels enough stuff has collected, it slowly reels the filament in towards its mouth.
Like reeling in a fish.
Kind of. Then it uses its arms to scrape all the collected gunk, the snow, the mucus, the bits off the filament, and then it mixes that gunk with even more mucus that it secretes from its own body.
More mucus. Why?
To bind it all together, it forms the whole collection into a neat little ball, a little package of food.
Wait, so it makes a marine snow mucus dumpling.
That's basically what it is. A self-made dumpling of detritus held together with slime, and then it pops that dumpling into its mouth.
Yum. Oh. But also, kind of brilliant. It uses almost zero energy to catch its food. Just waits for the delivery.
Perfect example of deep-sea energy conservation. Why chase a meal when you can let the buffet come to you and stick to your fishing line?
Okay, the vampire squid is officially way cooler and less scary than I thought. Who's next on the weird snow eater list? You mentioned mucus architects.
Yes. Let's talk about creature number 2, the snot palace architect, the giant larvation.
Snot palace architect. Okay, this sounds amazing already. What is a giant larvation? Is it giant?
Well, the giant part refers to the palace, not the creature itself. The larvation itself is actually pretty small, maybe just a few inches long at most. It looks kind of like a little clear tadpole swimming around. Nothing too impressive on its own.
A tiny tadpole building a palace.
Yeah.
Made of?
Made entirely out of its own mucus, its own snot. This is its superpower. It secretes this mucus and builds an incredibly complex, elaborate structure around itself. We call it its house, or more fun, its snot palace.
How big can the snot palace get?
Huge. Some species can build houses that are up to 3 feet across, all made of intricate filters and chambers constructed from slime.
A 3-foot house made of snot built by a tiny tadpole.
That's unbelievable. What's the palace for? Is it just a home?
It's much more than a home. It's a highly efficient food filtering machine. The little tadpole-like larvation lives inside, right in the middle, and it constantly beats its tail
Why does it beat its tail?
to pump water. It pumps huge volumes of water, like hundreds of gallons per hour, through the different layers and filters of its snot palace. The palace is designed with these incredibly fine mesh screens made of mucus
Screens to catch
the tiniest bits of food floating in the water, especially the very small particles of marine snow that other animals might miss. It's filtering out microscopic food particles. Wow, so it builds its own giant net out of slime to catch dinner. That's smart. But filters get clogged, right? What happens when the snot palace gets full of all that filtered gunk? Does it clean it?
Nope. Cleaning would take way too much energy. When the filters get clogged and the water flow slows down, the larvation does something remarkable. It just
It leaves. It abandons its giant snot palace.
completely abandons it. It can wiggle out in just a few seconds, leaving the entire clogged mucus structure behind. And then it immediately starts building a brand new snot palace from scratch, which it can do very quickly.
Okay, wait. So there are these giant abandoned snow-filled snot houses just drifting around down there?
Exactly. And this is where the larvation becomes another hero of the deep sea food web, because that abandoned house, it's now packed full of all the marine snow and tiny particles it filtered out of the water.
So like a giant snowball.
A giant sinking snowball. Because it's big and heavy with all that collected detritus, the abandoned snot palace sinks much, much faster than the tiny individual flakes it was made from.
Ah. So the larvation isn't just feeding itself.
It's acting as a marine snow repackager. It takes thousands of tiny, slow-sinking bits and concentrates them into one big, heavy, fast-sinking package.
Delivering a giant meal delivery straight down.
A huge, nutrient-rich meal delivered directly to the deeper parts of the ocean, maybe even straight to the seafloor, where other animals like those deep-sea sea cucumbers or even maybe our friend the vampire squid are waiting for a big score.
That's amazing. It builds a house to catch snow, then the house becomes snow food for others. What a cool cycle.
It's a beautiful, efficient loop. One creature's abandoned slime house is another creature's feast. It really shows how interconnected everything is down there and how important mucus is.
Okay, we've seen how marine snow feeds these incredible deep-sea creatures. But you said earlier it does something even bigger, something for the whole planet.
That's right. We need to zoom out now. Marine snow isn't just crucial for the deep sea. It actually plays a massive role in regulating Earth's climate. It helps keep our planet cool.
How can falling gunk cool the planet?
It's all about carbon. Remember we talked about carbon dioxide, CO2, in the atmosphere?
Yeah, you called it the planet's blanket. Too much makes the blanket too thick and the planet warms up.
Exactly. So we need ways to take some of that CO2 out of the atmosphere and store it somewhere else, somewhere safe for a long time. And the ocean is brilliant at this. It absorbs about a quarter of all the CO2 that humans put into the air.
Okay, the ocean absorbs CO2. Where does the snow come in?
The marine snow is the engine for a process scientists call the biological pump. Or an easier way to think about it is the carbon elevator.
Carbon elevator. Okay, I like that. Carbon is the Lego brick of life, you said.
It is. All living things are built with carbon. So the challenge is to get that carbon from the surface ocean, where it can easily exchange back into the atmosphere, and transport it down, deep down into the basement of the ocean building where it gets locked away.
So the elevator takes carbon downstairs. How does it work?
It's a simple three-step process, really. Step 1. Up in the penthouse, the sunlit zone, our tiny plant heroes, the phytoplankton, are doing photosynthesis. They breathe in CO2 from the water CO2 that came from the atmosphere. They use the carbon atoms to build their bodies and their shells. So the carbon is now captured, locked inside the phytoplankton.
Okay, carbon is in the plants. Step 2.
Step 2. The phytoplankton die, or they get eaten by zooplankton and turn into those lovely poop bricks. Either way, that carbon gets packaged into what will become marine snow. The snowflake is now the elevator car, and it's loaded with carbon.
Got it. Carbon package in the elevator car. Step 3.
Step 3. The elevator goes down. The marine snow sinks. As it falls, it carries that captured carbon away from the surface, down through the snack bar, down through the midnight zone. The sinking action is the pump. It's actively moving carbon downwards.
And where does this end up?
The carbon that makes it all the way down settles on the seafloor, becoming part of that thick, muddy layer called the ooze. And once it's down there, locked in the sediment, it can stay there for hundreds, thousands, even millions of years, safely stored away, unable to get back into the atmosphere and thicken the blanket.
Wow. So this constant snowfall is constantly removing carbon from the surface and locking in the deep sea. That's incredible.
It's one of the most important climate regulation processes on Earth. Scientists have estimated that without this biological pump, without this constant marine snowfall acting as the carbon elevator, the amount of CO2 in our atmosphere today could be twice as high as it currently is.
Twice as high, the planet would be so much warmer.
Much, much warmer. The deep sea, fueled by marine snow, is constantly working silently to protect us from runaway climate change, all thanks to this gentle, nonstop blizzard.
That puts a whole new perspective on things.
Yeah.
And didn't you mention something about desert dust helping this whole process? The ballast?
Yes, the ballasting effect. This is where it gets really cool, showing how everything on Earth is connected. Remember the ballast, the heavy bits like sand and dust that make the snow sink faster?
Yeah, helps it race past the snack bar.
Exactly. Well, the weather happening on land, thousands of miles away, can directly control how much food and how much carbon reaches the deep sea.
Oh. Give us that desert example again.
Okay, the Sahara Desert in Africa, it's huge, and it has massive dust storms. When these storms hit, winds can blow millions of tons of fine Saharan dust way up high into the atmosphere.
And the wind carries it.
Carries it right across the Atlantic Ocean for thousands of miles. Eventually, this dust settles out of the air and falls onto the ocean surface.
And gets stuck in the sticky marine snow.
You got it. It gets incorporated into the snowflakes as ballast. And this Saharan dust does two amazing things. First, the dust itself contains minerals like iron, which are like vitamins for phytoplankton. So when the dust falls, it can fertilize the ocean surface, causing a big bloom of phytoplankton. More plants.
More plants means more snow eventually.
Right. And second, all that dust is extra weight. It makes the resulting marine snowflakes super heavy, super ballasted.
So they sink.
Like rocks. They plummet down through the water column, zooming past the hungry gatekeepers in the twilight zone. This delivers a sudden, massive feast of carbon-rich food right down to the abyssal plains miles below.
So a dust storm in Africa can mean a surprise banquet for sea cucumbers 2 miles under the Atlantic.
Isn't that incredible? It's a perfect example of how connected our planet's systems are. Land, atmosphere, surface ocean, deep ocean, all linked by processes like dust transport and marine snow.
That is mind-blowing. And this snow has been falling for how long?
Oh, for millions and millions of years. This process is ancient, and we can actually see the evidence of ancient marine snow right here on land.
How? Where?
Have you ever seen pictures of the famous white cliffs of Dover in England? Those huge, bright white cliffs right by the sea?
Yeah, they're really white.
They are made almost entirely of chalk. Pure white chalk.
Okay, where did all that chalk come from? Don't tell me.
It came from marine snow. Hundreds of millions of years ago, that whole area of England was covered by a shallow, warm sea. And that sea was filled with trillions upon trillions of those tiny phytoplankton we mentioned earlier, the coccolithophores.
The ones that build little shields out of chalks.
Exactly. So for millions of years, as these tiny chalk-armored plants lived and died, their microscopic chalk shields rained down constantly onto the seafloor. Layer after layer after layer of a chalky marine snow.
Piling up like real snowdrifts, but underwater and made of chalk.
Precisely. And over vast amounts of time, the immense pressure from the layers above and geological processes squeezed all that chalky ooze together, pressing it into solid rock, the chalk rock that forms the white cliffs of Dover.
So those giant cliffs are basically ancient, squashed marine snow made of billions and billions of tiny plankton skeletons.
That's exactly what they are. They're a gigantic, visible monument to the power of marine snow and the biological pump over geological time, a massive carbon capture and storage system that nature built millions of years ago.
That is absolutely incredible. It makes you think about how important this whole system is. But is it okay? Is this marine snow process healthy today?
That's a really important question. We've talked about how amazing and vital it is, but it's also quite sensitive. Remember that great race against time, whether the flake sinks fast and locks carbon away or gets eaten near the surface.
Yeah, the fast sinkers are good for climate and the deep sea.
Right. But unfortunately, some human activities seem to be interfering with that race, maybe slowing things down or changing the snow itself.
Like what?
Well, think about pollution, like excess fertilizers washing off farms into the ocean. This can sometimes cause huge blooms of algae, but sometimes they can be harmful or toxic algae. When those algae die and sink,
It becomes toxic snow.
exactly, toxic snow raining down, potentially harming the creatures that eat it, all the way down the food web.
Yikes. What else?
And then there's the issue of plastics. We know our oceans, sadly, have a lot of plastic pollution, and it breaks down into smaller and smaller pieces called microplastics.
Tiny bits of plastic.
Tiny bits. And guess what? These microplastics are just the right size and density to get easily caught up in that sticky teppy, the ocean glue.
Oh no. So plastic gets stuck in the marine snow.
It does. It literally hitchhikes a ride on the marine snow elevator, carrying plastic pollution all the way down to the deepest parts of the ocean, places we once thought were pristine. The creatures down there waiting for their food delivery might be eating plastic instead of, or along with, their usual meal.
That's awful. So we're changing the snow itself and maybe even how fast it sinks.
It seems likely. We're still learning exactly how all these changes, pollution, plastics, warming waters, ocean acidification, are affecting the marine snow cycle and the biological pump. But it's clear that this vital global system is facing new pressures.
Wow. We started this whole journey today imagining William Beebe, that first snow watcher, peering out of his tiny bathysphere window.
And we ended up discovering this incredible planet-connecting blizzard, this continuous snowfall that is the floating buffet for the Earth's largest ecosystem.
And one of the most important climate helpers we have, keeping our planet cooler by acting as a giant carbon elevator.
It really shows how everything is linked, doesn't it? What happens in a desert thousands of miles away, or what chemicals wash off a farm, or even what a tiny tadpole-like creature builds out of slime. It all connects and impacts the entire planet.
Nothing in the ocean is really waste, is it? One creature's poop brick or abandoned snot palace is vital fuel for another creature's survival.
It's the ultimate recycling system.
So, thinking about the future, that great race against time for the snowflake and how human actions might be slowing it down, it's definitely something to keep in mind.
It really is. The future of this amazing, hidden, vital system really depends on us understanding it better and on the next generation of explorers and scientists, maybe even some of you listening right now, to keep asking questions, keep learning, and help protect this mysterious, wonderful world beneath the waves.
We really hope this story of the hidden blizzard, the marine snow, gives you something magical and maybe a little bit gross to think about next time you look out at the big blue ocean. Remember that whole world of wonder falling silently below.
Thank you all so much for exploring this incredible story with us today. It was really fun.
It really was. See you next time on Saltwater Stories.